Hi there! In our last lesson, we entered into a brand new framework in which interest rates are no longer constant nor deterministic, but we play with stochastic interest rates. We have seen that there are different models that can be used, for example, the Vasicek model, to try to replicate what we observe empirically on the market for what concerns interest rates. Now, the problem of introducing stochastic interest rates is that the framework we have been considering until now needs to be updated. For example, the Cameron-Martin theorem no longer holds. What we have to do is to introduce a generalization of the theorem that goes under the name of Girsanov theorem. The Girsanov theorem is the theorem that allows us to build a connection between a Brownian motion with drift, when the drift is a process itself, and a Brownian motion. Again, using two different measures. What we will need will be a Radon-Nikodym derivative that connects the two measures. In the standard Cameron-Martin framework, we have seen that this Radon-Nikodym derivative is the exponential martingale. In the Girsanov setting, we will introduce the so-called generalized exponential martingale. We will see that since we generalize and we introduce a drift that is a process, we will have to take care of some problems. Remember that in the Ito calculus setting we are playing with, we always have to guarantee that the Ito integral is well defined. That's why, for example, we will introduce conditions about the drift belonging to specific classes. You can imagine the M2 or the H2 class. And we will also impose some extra conditions for what concerns the existence of moments. There are many different conditions in the literature. Here we will consider probably one of the strongest ones, that is to say, the Novikov condition, that allows us to simplify a little bit the treatment. In reality, for what concerns the proofs we will consider together, we will even make things more and more simple by making assumptions about deterministic components and so on. But the philosophy of the proofs we will consider is exactly the one that you should also follow in the more complicated settings. So let's start our lesson. We start by considering a stochastic process psi t over the time interval 0 capital T. Okay, so our standard maturity framework. Okay, we ask this process psi t to belong to the H2 class, that is the most general class that we have considered together when discussing the Ito integral. In reality, if you want, you can also consider more general situations, but for us, psi belongs to H2. And we also require that psi is adapted to what? To the natural filtration generated by the Brownian motion we will play with in the rest of the lesson. Okay? So this is our basic setting. Now, given this process psi, we can always define an Ito integral that involves the process. So we can take, for example, the integral between 0 and t of psi s dbs. And this integral, if psi belongs to the H2 class, is well defined. Now, this said, let's define the following new process. It's the process zt, which is nothing more than the exponential of what? Of the difference of two integrals. The first part is the Ito integral of the process psi over the interval 0t, and the second part is minus 1 over 2, the Riemann-Stieltjes integral over the interval 0t of psi squared. Okay, this quantity zt will be what, if we add extra condition, will represent the generalization of the exponential martingale. And that will be what we will call the generalized exponential martingale, because we know that us mathematicians have a lot of creativity and fantasy in given names to things. In order to guarantee that the process zt that we have just defined is a proper Radon-Nikodym derivative, we need some conditions. There are many in the literature. As I told you, we have chosen to use the Novikov one. The Novikov condition guarantees that actually zt is a generalized exponential martingale and can play the role of a Radon-Nikodym derivative to move from the measure p to another measure that we will use in our setting. We will see that not necessarily this new measure would be the risk-neutral measure, but we can have also the forward measure and so on, because we know that in dealing with stochastic interest rates, the risk-neutral measure per se is not always sufficient. Okay, the Novikov condition at the end of the day is nothing more than a condition on the existence of the second moment. As you see on your screen, the Novikov condition requires that for every t in the time interval 0 capital T, we have the following. The expectation of the exponential of the Riemann-Stieltjes integral between 0 and t of psi s squared ds is finite. Then we can also add a 1 over 2 in the integral just to take care of some coefficients that we will observe later. But in a sense, we are just requiring that this second moment condition is guaranteed, and we have that the second moment is finite. Remember that psi itself is a process. And if you go back with your mind to what we said at the very beginning when we were discussing Ito integrals, remember that in our setting we want to play with integrals for which the mean and the variance, remember that an Ito integral is a random variable, we want to play with integrals for which the mean and the variance are well defined. Now, for what concerns the mean, it's not a big deal. We know that the expectation is always equal to 0, but for what concerns the variance, we have to rely on the Ito isometry, and now you understand the Novikov condition. If the Novikov condition is satisfied by the process psi, then we have that the quantity zt is a proper Radon-Nikodym derivative, because the expectation of zt is always equal to 1 for every t, and we also have that the process zt is a positive martingale with respect to the natural filtration generated by the Brownian motion that we have embedded within zt. Now, proving that zt is always positive is trivial. Just remember that we are considering the exponential of something, so by definition, this is positive. To prove that it is a martingale, so that the process zt is a martingale, essentially we can mimic what we did for the Cameron-Martin theorem. In particular, if we consider the simpler case of psi being deterministic. So not constant as it was in the Cameron-Martin theorem, but deterministic, in which psi itself does not involve any particular randomness. The proof in the more general setting of randomness is essentially the same, but you need some extra subtle steps that I prefer to skip. And in any book on stochastic calculus you find that, but it will take too much of our time. In any case, in chapter 5, here in this setting we have a sort of flashback to chapter 2, to the end of chapter 2 in our lecture notes, but in chapter 5, in a sense, if you go and you consider the proof of the Girsanov theorem as stated in chapter 5, or Girsanov 1 as we call it, then you will also see the general setting for the Novikov condition in the case in which, for example, the process psi is bounded. But in any case, in what follows, we will just consider psi to be deterministic. And for the martingality part, I leave that to you because the proof is exactly the same as the proof that we had for Cameron-Martin. What I want to observe with you, not because it is particularly difficult, but as a way to refresh some important results, we want to prove that the expectation of zt is always equal to 1. so that Zt, which is a positive martingale with expectation equal to 1, is a proper Radon-Nikodym derivative. Okay, so we consider the case in which psi is a deterministic quantity. Okay, so it can vary over time, but deterministically. If this is the case, we have that the Ito integral between 0 and t of psi s dbs is normally distributed with mean 0 and variance equal to the Riemann-Stieltjes integral between 0 and t of psi s square ds. Okay, and this last thing comes from a simple application of the Ito isometry, as we have done several times in our previous lessons, in particular at the beginning of our course. Now, if we want to compute the expectation of Zt, what we do, we just compute the expectation of the extended definition of Zt, so we just write it down, is the expectation of the exponential of the difference of the t integrals, the Ito integral and the Riemann-Stieltjes integral, and then we can do the following. We can just rearrange the terms by splitting the difference of the two integrals as the product of the exponentials of the two integrals. And we can notice that the second integral, the Riemann-Stieltjes integral, actually is deterministic, so we can take it out of the expectation. What remains is the expectation of the exponential of the Ito integral. Now, what we have just said is that the expectation of the exponential of the Ito integral is the expectation of the exponential of a normally distributed random quantity. And as we have done several times in our course, we recognize that this is the log-normal expected value. So we can actually immediately solve this expectation, and this expectation is the exponential of what? Of mu, but mu is equal to 0, sigma squared over 2. So sigma squared over 2 is just 1 over 2, and then we write the variance. What we get is actually that the two exponential terms now are just compensating one another, so that the product of the two exponential is equal to the exponential of 0, which is just 1. If the process Zt is a proper Radon-Nikodym derivative, we can use this Radon-Nikodym derivative to move from the measure P to another measure. How? As we did for the Cameron-Martin framework, is exactly the same thing. So we take our process Zt and we consider the value Z capital T. After that, we can define for every event f, Q of f, so the measure of f, the new measure Q, as the expectation under the measure P of what? Of the indicator of the event f times Z capital T. This is a new measure defined via the Radon-Nikodym derivative that depends on the generalized exponential martingale process Zt. Given the process Bt, so our Brownian motion, we can define a new process B tilde T. And this new process is a Brownian motion with drift, but a special Brownian motion with drift. It is equal to Bt, the original Brownian motion under our physical measure, minus the integral between 0 and t of psi s ds. What we would see is that Girsanov gives us a way of connecting this Brownian motion with drift under the physical measure with a standard Brownian motion under the new measure Q. Indeed, a first simple enunciation of Girsanov's theorem is what you see on your screen. Under the measure Q, the process B tilde T is nothing more than a standard Brownian motion. As we did for the Cameron-Martin theorem, we can play with the moment-generating function. And what we want to show is that when we consider the increments of B tilde t, that is to say, if we consider a partition, we consider bt1, bt2 minus bt1, bt3 minus bt2, and so on until we reach btn minus 1. Okay, if we consider these increments and we consider under Q the moment-generating function of these increments, this moment-generating function corresponds to the moment-generating function of n independent normally distributed random variables with mean equal to 0 and variances equal to t1, t2 minus t1, t3 minus t2, and so on until tn minus tn minus 1. Okay, so we want to show this. Now, what you see on your screen is just the formalized representation of what I just told you. So we take the expectation and the Q of our increments of the bt tilde Brownian motion, and we look at the moment generating function of n independent normally distributed random variables and blah blah blah. To simplify the proof, we will just consider the case of one single increment, as we did for the Cameron-Martin theorem. So we just consider t1, so we can even drop the 1, so we just consider t, so we consider bt, that is the increment between 0 and t, and we show that actually this corresponds to the moment generating function, if we play with this increment, of a normally distributed random variable with mean 0 and variance equal to t. Okay, the proof is very simple, and we'll do that in a few steps. Since we just consider one increment for the process b tilde t, its moment generating function under Q is the expectation under Q of the exponential of alpha b tilde t. Now we can just substitute the definition of b tilde t, that is our Brownian motion with that integral drift, and we just obtain what you see on your screen. So the expectation under Q of the exponential of alpha bt minus alpha, the integral between 0 and t of psi s ds. The expectation under Q can be given in terms of the expectation under P once we also introduce the Radon-Nikodym derivative zt stopped in T. And this is the second exponential term that you see in your equation. A simple collection of the terms in dBs and in ds gives us the possibility of obtaining the third line of our equation. We can then notice that within the Riemann-Stieltjes integral there is a term 2 alpha psi s plus psi s squared. And this could be completed if we could have an alpha squared terms divided by 2, because remember that the Riemann-Stieltjes integral is in reality divided by 2, so there is one half in front, or ds divided by 2, as you prefer to write it. So if we add and remove an alpha square over 2 terms, what we have is that the part in the Riemann-Stieltjes integral can be completed, and we can write that as alpha plus psi s everything to the power 2, and we remain with a term minus alpha square over 2. But this term, once taken out of the integral by solving the integral and looking that in front of the integral we have a minus sign, just can be taken out of the expectation. Why? Because it is totally deterministic, and this term is exactly the exponential of alpha squared over 2t that you see in front of the expectation remaining. Now, notice that what remains, the expectation under p of the exponential of the difference of these two integrals, in which the process psi s now becomes alpha plus psi s, is nothing more than an exponential martingale, a generalized exponential martingale. And the nice thing is that we know that this quantity here has an expectation equal to 1. It means that what remains is just the exponential of alpha squared over 2 times t. And our proof is complete. In chapter 5 of our lecture notes, you find some generalizations of the simple Girsanov theorem that we have just considered. You see, for example, what happens when you use a little bit more complicated processes for what concerns the psi term. You also see what happens when you do not only play with the drift, but you also introduce variability in the diffusion part of your Ito process, up to the third version, Girsanov 3, that is extremely general and extremely complicated to be proven, that we just state without any proof. And already for Girsanov 2, you can totally ignore the proof. What is important is that in those enunciations of the more general Girsanov theorem, you can see the actual power of the process. For the remaining part of the course, they are even probably too powerful, but it's important that you have them there in the lecture notes as a reference for you.